You've practiced part-to-whole relationships, ratios, and fractions. Well, in this lesson, we're asking what is a directed line segment and what does it mean to partition it? So next what we're going to do is we're going to use ratios and fractions to find the coordinates of a partitioned directed line segment. Let's go ahead and get started. A directed line segment is a line segment that has a direction. And we can see right here that we've got three examples of directed line segments that I'd like to tell you a few things about. First up, all directed line segments have two endpoints, just like an ordinary line segment. And we can see them right here. We think of those endpoints as being part of the directed line segment. Directed line segments also have a direction, and we indicate that direction with the arrow on the tip. So that means that the entire directed line segment consists of the starting point all the way up till the ending point. And we really want to go, when we think of the directed line segment, in the direction indicated by the arrow. One of the things that we can do with a directed line segment is partition it. And to partition something means that we break it in pieces. And we're actually going to be breaking it into pieces in a way that makes us concerned about the length. And when we do this, the direction of the line segment is going to be very important to us. Let's see an example. Here we're asked to place point P so that it partitions the directed line segment that goes from A to B, and we want it to be in a 2:5 ratio. So what we need to do here is place a point somewhere along that directed line segment that makes it so that the length of the line segment on the left has 2 units to it, and on the right, we want it to have 5 units, just like that point that I drew. So we can call that point P. Remember here that the direction was important, and the way that that was important is that I started this ratio by traveling in the direction of the arrow from the starting point until I got to 2 units, and then I finished up the 5 units until I got till the end of my directed line segment. Had I been asked to do this in a 5:2 ratio, that would have been an entirely different problem, but I would have started at the starting point, A, and traveled along until I met 5 units. So there's 2, 3, 4, 5. And I would have placed a point right there. When I do that, I can see that I've got 5 units to the left and 2 units to the right, once again for a total of 7 units. But that is a totally different problem. We were asked to do it in a 2:5 ratio, and point P does the trick. We're going to partition a directed line segment in the coordinate plane. And we're going to do this in a way that's totally general. So in doing this, we'll actually derive what's called the section formula. Here we're given a directed line segment that goes from A to B. And I can see that because we're doing this in general, I've got the unknown variables x1, y1, and x2, y2 for the coordinates of A and B. We're asked to find the coordinates of point P, which partitions the directed line segment in the ratio m to n. We don't know the coordinates of point P, but we do know that we're considering the case in which P is right on the directed line segment. So we can draw it on the directed line segment and say that its coordinates are x, y. When we do that, I know that the ratio of line segment AP to the length of line segment PB will be in the ratio m to n. Next, what I want to do is create some similar triangles in a special way. First up, I'm going to draw PC and BD that are parallel to the y-axis. Now, points C and D are going to have some special properties. Here's line segment PC. It's parallel to the y-axis, and notice that it has the same x-coordinate as point P and the same y-coordinate as point A. Furthermore, I can do this with BD, just like this. Now, this line segment has the same x-coordinate as point B and the same y-coordinate as point P. Now what I can do is draw AC and PD that are parallel to the x-axis. I know that these line segments will be horizontal because of the way that the y-coordinates of D and C match P and A, respectively. Since the x and y axes are perpendicular to each other, and these line segments are drawn parallel to the x and y axes, I know that these are right angles. And therefore, I have two right triangles. Furthermore, I notice that the directed line segment AB is a transversal of the parallel line segments that go PC and BD. If we remember what we know about transversals, then I can say that, hey, these are corresponding angles and therefore they're congruent. And now when I investigate these two triangles, I see that I have got angle-angle congruency, and, angle-angle similarity, and therefore the triangles are similar. We can use that because we know that the side lengths of similar triangles must be in ratio, and we already know the ratio between two of the side lengths in these triangles, specifically the hypotenuses. Let's take a closer look. Here, we've written out all the different ratios of corresponding side lengths, and since I know that this point P must have broken that in the ratio m to n, I know that all these ratios must be equal to m over n. Therefore, if I could solve for just one of these ratios, like I'm doing down here, I would be able to get specific coordinates for x and y. In particular, I know AC and PD. The reason I know the lengths of AC and PD is because they're horizontal line segments and I know their coordinates. I can just subtract the x coordinates in order to find their lengths. So therefore, by the substitution rule, AC over PD is equal to m over n. And if I look at that, I notice that, hey, I can solve now for x. Let's take a closer look. My first step is to simply cross multiply. After cross multiplying, I end up with this equation right here. And what I'm going to do is distribute n and m into the parentheses. That'll give me n times x minus n times x1. And that equals m times x2 minus m times x. At this point, I'll bring all of the x's to one side and all of the x1, x2's to the other. So that'll give me n times x plus m times x. And this will be equal to m times x2 plus n times x1. If I take a close look at that left-hand side, I see that I can factor out x. And let's go ahead and do that. Let's use a new color. I factor out x, and what I'm left over with is n plus m. The right-hand side hasn't changed. Now what I'll do is I will divide both sides by n plus m, and when I do that, I discover that x is equal to m x2 plus n x1, and all of that will be over n plus m. That's actually the x coordinate of P, if P is breaking the ratio in an m to n ratio. I could have worked in a very similar way, specifically with these line segments, in order to find y. When I do that, I would discover that y is equal to m y2 plus n y1, and that'll all be divided by n plus m. So there you have it. We found the x and y coordinates of point P, and that actually gives us the section formula. The section formula can be used to find the coordinates of the point that partitions a directed line segment in a given ratio. Let's start off by saying that x1 and y1 are the coordinates of the endpoint at the start of the directed line segment. x2 and y2 will be the coordinates of the endpoint at the end of the directed line segment, and we'll say that we're partitioning it in the ratio m to n. Well, in this case, we already know that we've derived a section formula that says that the x coordinate is equal to m times x2 plus n times x1 all over m plus n. And the y coordinate is given by m times y2 plus n times y1 all over m plus n. This is a great formula we derived, but if we manipulate it algebraically a bit, we can end up with the set of equations that we see on the right-hand side. And that's the set of equations that I want to focus on. So write this down if you need it. I'm going to clear the screen and focus in. In these equations, notice that we've got x2 minus x1. That gives me horizontal change. We've also got y2 minus y1. That gives me the vertical change. When I multiply these by m over m plus n, that gives me a fraction of the directed line segment, specifically the fraction with length scaled down by the ratio m to n. Bear in mind that m over m plus n is actually the part-to-whole relationship representing that same exact ratio. After we've done that, what we do is we add on the initial point by adding on x1 and y1. Those are the coordinates of the starting point of the directed line segment. When we have the formula in this form, it is pretty straightforward to use. Let's take a look at an example. Here in this problem, we're asked to find the coordinates of a point E that divides the directed line segment that goes from F to D in the ratio of 2 to 7. We can use this rewritten section formula, and for this one in particular, I need to know that m is 2. I need to know that n is equal to 7. It looks like I also need x1 and x2. I can read that from the graph. Here's the directed line segment going from F to D, and x1 will be the x-coordinate of the beginning point. That's equal to 3. x2 will be the x-coordinate of the ending point. That's negative 4. So now when I put this stuff into my equation, I have that x is equal to 2 over 9ths. 2 plus 7 is 9, so it reduces down to 2 9ths, times x2 minus x1. Well, here's x2, that's negative 4, minus x1 is 3. Then what I do is I add on x1, which is equal to 3. You take that arithmetic expression and simplify it, and what you'll get is 13 ninths. Exactly. We're not done yet because we're doing this in the coordinate plane. We just found the x-coordinate of point E. We need to find the y-coordinate too. Luckily, we've got a section formula for the y-coordinate. In this case, we still need that m is 2 and n is 7. But now we need the y-coordinates of the beginning and ending points. Well, F is the beginning point, and its y-coordinate is equal to 1. D is the ending point, and its y-coordinate is equal to negative 3. So I substitute all this information in, and I'll get 2 ninths times y2 minus y1. Well, that's negative 3 minus 1. Now I add on y1, so plus 1. If I take that, simplify it down, what I end up with is 1 ninth. So this tells me now that the coordinates of point E are given by 13 ninths and 1 ninth. Now if I were to plot that, 13 ninths is equal to about 1.4 in the 4 repeats. So that puts me right about here. And that does look to me like it breaks the directed line segment in the ratio of 2 to 7. Now had I been working in the number line as opposed to the coordinate plane, well, I would have been done when I found the x-coordinate because the number line is one-dimensional. There's just one coordinate to find. However, here, I was in fact working in the coordinate plane, so I defined the x and y coordinates. Take all of the stuff that you've learned so far and now practice this on your own. We're going to go ahead and use the section formula to find the midpoint of a directed line segment. Remember, the midpoint is equidistant from the endpoints, meaning that it breaks it into 2 equal parts. And so the fraction that we'll be using is 1/2. And what I'm going to do is I'm going to use the section formula, which gives me formulas for x and y in the form m over m plus n. And for x, it'll be x2 minus x1 plus x1. And for y, I'll still have m over m plus n, but this time it'll be y2 minus y1 plus y1. Go ahead and write those formulas down because I'm going to clear the screen and make room for these calculations. x1 and y1, well, those are up there at Q, the start of my directed line segment, and I see that they have that point has coordinates negative 3, 4. x2, y2 are the coordinates of point R, and I can see that those are at 3, negative 3. So based on the formula that we're using, x is given by 1/2 times x2 minus x1. So that'll be 3 minus negative 3 plus negative 3. And when I simplify all that down, I get 0. Y, on the other hand, that'll be 1/2. And now I'll subtract the y coordinate. So that'll be y2 minus y1. That's negative 3 minus 4 And what I add on is y1, which is 4. When I simplify that expression, what I get is 1/2. Therefore, the point P, such that P is 1/2 the length of the directed line segment, that is to say that P is the midpoint, it has coordinates 0, 1/2. That's point P. And if I were to plot point P, I can see it's right there. And examining this, I can see that it does, in fact, serve as the midpoint of my directed line segment. In this lesson, we're asking, what is a directed line segment and what does it mean to partition it? Well, actually, we've learned a formula for partitioning a directed line segment that looks like this. And what we're going to do next is we're going to see how partitioning a directed line segment can help us to solve some problems. We're going to partition a directed line segment in order to solve a problem. Here, Amanda has a 24-inch board and she wants to cut it in a ratio of 2:5. However, she has 3 inches of rotted wood at the end of the board, and so she's going to have to start by cutting that off. If we think of this like this, we can think of the board as extending from 0 to 24, because it's a 24-inch board. However, she needs to lop off those 3 inches, so it'll start at number 3 right there on the number line, and then extend out to 24. And we want this finally to be in the ratio of 2:5. So we're trying to find a point somewhere in here that'll split that directed line segment in the ratio 2:5. Well, where will that point be? We can use this formula that says x will be given by m over m plus n times x2 minus x1 plus x1. In this case, we're cutting it in the ratio 2:5. So that means that m is 2, and then n is 5. So on the denominator, I'll have 7. x2 is 24, and x1 is 3. So that'll give me 24 minus 3, and then we add on 3. Simplifying this, I get 2/7 times 21 plus 3, which simplifies down to 9, which means that her cut will be located right here at 9 along that directed line segment. And when I take a look at that, I can see, in fact, there are 2 units on the left of that point, and there are 5 units on the right. So this is, in fact, a 2:5 ratio that she has cut the line segment. I'm going to show you how we can apply partitioning to a real-life example. Here we're told about this guy, Jake, and he kayaks across a lake in a straight line from point A to B. We can represent his path with a directed line segment. Well, along the way, he stops for lunch on an island, such that the distance from point A to the island and the distance from the island to point B is in the ratio of 4:3. So that means that the distance from right here to the distance from the island to point B right there is in the ratio of 4:3. We're asked, what are the coordinates of the island's location? Please round to the nearest tenth. Well, let's do this with the section formula. M is equal to 4. N is equal to 3. So that means that M over M plus N is equal to 4 over 4 plus 3, which is equal to 4/7. So applying the section formula now, I need also to know the coordinates of the ending point, x1, y1. That's right on the origin, so I can see that that's 0, 0. The coordinates of, that's the coordinates of the starting point. And the coordinates of the ending point, b, well, those are 5, 2. Those are my x2, y2 values. So using these values in my section formula, I'll have that x, the x coordinate of the island's location, is 4/7 times x2 minus x1. That's 5 minus 0 plus x1, which is 0. And you simplify that, you get 20/7. This is my x value. For y, I have, once again, 4/7. But now I'll go y2 minus y1. That's 2 minus 0 plus y1. That gives me plus 0. And it all simplifies down to 8/7. Remember, we were asked to round to the nearest tenth if necessary. So when I do that, my answer is about 2.9 and 1.1. Those are the approximate coordinates of the island's location. And if I plot those on the directed line segment, I can see that that point will be about right there. And that is the point that is 4/7 along the way, along the path, along the directed line segment. And it's 4/7 of the way along because we broke the line segment into a ratio of 4:3.